And good day everyone, Mr. Armkey back with you for Net 125. Today we're talking about Module 8, the network layer, also called Layer 3. So we're going to look at some network layer characteristics today, how the network layer uses IP protocols for reliable communication, although as we recall, IP is not a reliable protocol in and of itself. We're going to look at the IPv4 and IPv6 packets as well as their structure and their roles in transmission. How a host routes. We're going to talk about network devices using routing tables to direct packets to a destination network. So this is inter-network communication rather than local network communication, which is what we talked about when we were discussing switching. And then we're also going to talk about the fields in the routing table of a router. So let's talk about network layer characteristics first. The network layer provides services to allow end devices to exchange data. IPv4 and IPv6 are our principal Layer 3 protocols. Layer 3 handles four basic operations: end device addressing, encapsulation, de-encapsulation, and routing. So encapsulation and de-encapsulation are the same process, they're just performed in reverse order. So encapsulation is the process of adding headers, or in the case of Layer 2, a trailer, to a PDU as it transverses the layers in order to add information about how to route or process that particular PDU. IP can use either version 4 or version 6 and not have any impact on the Layer 4 segment. Now the IP packet is examined by all Layer 3 devices as it traverses the network. If we're talking about Layer 2, then that's going to be the frame, as you recall. IP addressing does not change from source to destination, except in the case of what we call NAT, but that is, again, not necessarily a change as much as it is just a translation. IP is meant to have low overhead and may be described as connectionless, best effort, and media independent. It is not locked to a particular form of media transmission. IP is connectionless, which means that there will be no connection established before sending the packet to the destination. There's no control information such as synchronization, acknowledgements, or the other handshakes that we expect with TCP. The destination receives the packet when it arrives, but there are no pre-notifications. And if there is a need for connection-oriented traffic, then we handle this at Layer 4 with TCP. In the graphic here, we see a letter being put in a mailbox and arriving at the destination. What happens in between is immaterial. As long as it goes from one place to the next, we have considered it to be a successful delivery. As IP is best effort, we have to be aware that IP does not guarantee delivery. It has reduced overhead because there's no mechanism to resend data once it is not received. If we want to, again, rely on these fallbacks for correcting a potentially erroneous transmission, we have to rely on something at Layer 4. IP does not expect acknowledgements either. It doesn't know if the other device is operational, if it received the packet, or if it routed it correctly once it arrived. It's basically just a big game of pass the parcel, if you will, or hot potato. We're going from one person to the next, and we have zero control over what the other units in that particular link or path are going to do. IP is unreliable, which means it cannot fix itself or manage any kind of undelivered or corrupt packet. It can't retransmit after an error, it can't realign any packet that's out of sequence, and it has to rely on other protocols for these functions. IP is also media independent, meaning that it doesn't concern itself with the type of frame that it needs at Layer 2 or the media type that it uses at Layer 1. We can send IP over copper, fiber, or wireless with no impediment to the actual transmission. Media independence also means that the network layer will establish the maximum transmission unit size, or MTU. This is going to be received from control information sent by the data link layer. The network then establishes the MTU size based on that infrastructure. So again, remember, anywhere between 64 and 1518 is considered a standard frame size, but the maximum transmission unit can of course be modified depending on the infrastructure with which we work. Fragmentation is when Layer 3 has to move the IPv4 packet into smaller units. Fragmenting can cause latency because, of course, we're then taking a single packet and moving it into a smaller unit. IPv6 does not do fragmentation. That's only something that we deal with Layer 3. So an example of this would be a router going from Ethernet to a slower WAN with a smaller MTU. So let's say that we have something that's calibrated for the full 1518, but then we kick back and then the next WAN we hit has an MTU of around 1300. We have to figure out what to do with the extra, 220 bytes or so. It's a pretty big change, so we have to make sure that we split it accurately and can reassemble it the other side. So let's take a look at IPv4 first. That's the more common one you'll deal with because IPv6 is still in transition. IPv4 is the primary protocol for the network layer, and the header for IPv4 has many purposes. It ensures that the packet is sent in the correct direction. We want to go forward, not back, of course. It contains information for network layer processing in various fields, and the information in the header is used by all layer 3 devices that handle the packet. That is something you're going to want to make sure you familiarize yourself with as you're working with OSI, is knowing at what layer something is going to be interacting with a PDU. The characteristics of the IPv4 network header are as follows. It is in binary, simplifies the overhead, and contains several fields of information written at, in this diagram at least, left to right, 4 bytes per line in order to comprise the entire 20-byte header. Protocols may have one or more functions involved, but as always, the source and destination are going to be the most important for IPv4. All these various options, if you will, are not going to be anywhere near as necessary as being able to process the correct source and destination. So the header fields that we see, the optional stuff, will be version, of course. Version 4 will represent itself as 4 in binary, or 0100. V6 would be 0110. Differentiated services used for quality of service. Header checksum in order to detect corruption. The time to live, which gives us the hop count. Hop limit would be the IPv6 equivalent. The protocol, which tells us what we're dealing with at layer 4. The source and destination IPv4 addresses, which are pretty self-explanatory. Now let's take a look at IPv6, the more modern version. IPv4 has 3 major limitations. IPv4 is essentially built on a 32-bit standard protocol that gives us about 4.3 billion addresses globally. So we've essentially run out. We also don't have a lot of what's called end-to-end connectivity with IPv4. We have to instead establish private communication and addressing through what's called NAT, Network Address Translation. This translates a local IP address in a private network to a public IP address. Direct communications with public addressing was essentially no longer necessary. It just provided a single interface for that exterior of the LAN. NAT was meant as a temporary solution, and it creates network issues because we're manipulating network header addressing as it moves from one point to another. NAT causes latency, causes overhead, and it causes troubleshooting issues. IPv6 was developed by the Internet Engineering Task Force, also called the IETF. IPv6 overcomes the limitations we were just discussing by expanding the address space, improving packet handling, and eliminating the need for NAT. We now have addresses that are 4 times the length, a simplified header with fewer fields for lower overhead, and we have no NAT necessary because of the huge addressing space involved. So when we look at IPv4 versus IPv6, as I said, IPv4 falls into the around 4.3 billion range. So that's 10 to the 9th, 4 times 10 to the 9th. When we're talking about orders of magnitude, the front number is really not as important. On the other hand, when we look at 10 to the 36th power, meaning that we have 37 zeros following the 1 at the front, there are 340 undecillion IPv6 addresses. So that means that we have on the order of a massive fold of how many times we have. We have a cubed reference beyond that, a quartic, if you will. So 4 billion versus 340 undecillion, that's a lot of zeros difference. So of course we don't need NAT anymore. The IPv6 header is simplified, but that doesn't mean that it's smaller. Because the addresses are so much longer, now what would have taken up 32 bits is going to take up 128. The header is fixed at 40 bytes or octets in length, and several fields were removed or otherwise altered to improve performance. So things like the flag, the fragment offset, and the header checksum, no longer necessary. So here are the flags that we have retained, or the fields we've retained rather. Version 6, as I said, represented as 0100. Traffic class is now the equivalent of differentiated services. The flow label allows us to handle identical flow labels the same way. So this is kind of a prioritization or categorization field. The payload length tells us how big the packet is in the actual data portion. Tells us what our next level protocol should be at layer 4. The hop count has been replaced with the hop limit. TTL has gone away. Destination IPv4 and IPv6 addresses are now going to be transposed as well. I apologize for the graphic reading IPv4, it should say IPv6, but the bit length in the description is correct. IPv6 may also contain what are called EH, or extension headers. The characteristics of these are to provide additional network layer information. They are entirely optional. They're placed between the IPv6 header and the payload, and they may be used for fragmentation, although fragmentation really isn't a process that IPv6 currently has to do. It may also be used for security, mobility support, etc. So these extension headers are just options that are there in case it's ever needed. So let's look at how a host routes a particular data packet. Packets are always created at a source. Makes sense, right? Host devices then create their own routing table, and a host can send packets to the following items. Either itself, using the loopback address 127.0.0.1, or :1 IPv6, which is all zeros except for the 1. Local hosts, this is where the destination is on the same LAN, or remote hosts, which is where they're not in the same LAN. So rather than categorizing things into a very narrow set of things, we're doing a very broad set. The source device determines whether the destination is local or remote, and will use its method of determination based on what version of the IP protocol is involved. In version 4, the source uses its own IP address and subnet mask along with the destination IP. In version 6, source is going to use the network address and prefix advertised by the local router. Local traffic is dumped out the host interface to be handled by an intermediary, and remote traffic is forwarded directly to the default gateway on the LAN. And this is a big part of why having your default gateway established correctly is so important. The default gateway is an object that can handle communication between the local network and an external network. A router or layer 3 switch can act as the default gateway. Its features are that it must have an IP address in the same range as the rest of the LAN. It's usually the first available host address. It can accept data from the LAN and is capable of forwarding traffic from the LAN, and it can route to other networks. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the LAN. So we have to have that address preset in order to handle traffic that moves outside of a local network. The host will know the default gateway either statically or through DHCP. IPv6 sends the default gateway a message through what's called either router solicitation or manual configuration. Router solicitation is part of DHCP v6. A default gateway is a static route which will be the last resort route in a routing table. So if all else fails, it goes to the default gateway. All devices on the LAN will be need the default gateway of the router if they intend to send traffic remotely. So we have to establish that, again, very early on. In order to view a routing table, in a Windows machine at least, we can go in to route print or netstat-r, and that will give us our routing table. There are 3 sections that are displayed by these 2 commands. The interface list, which gives us all potential interfaces in MAC addressing, and the IPv4 and IPv6 routing tables. So on the right-hand side, we can see the IPv4 routing table for PC1. We can see its destination, the network mask that's involved, the default gateway, the interface that it is using, and its metric of worthiness or trustworthiness. So let's get into routing here in 8.5. When the router receives the frame from a host device, we are going to essentially de-encapsulate layer 2, the header and trailer, and then router 1 is going to examine the destination address at layer 3 and look for its best match in the IPv4 routing table. The route entry that we have, if we look at the left here, we can see our routing table, indicates that this packet is to be forwarded to router 2. So we're going to see that that is the third line in the routing table, and we know that its entry interface moves outwards at 10.1.1.0/24. Router 1 is now going to re-encapsulate the packet into a new Ethernet header and trailer and forward the packet to the next hop router, R2. This process, of course, will continue until it reaches the correct destination. So there are three different types of routes in a routing table. What's called a direct route, a remote route, or a default route. Directly connected means that these routes are automatically added provided that the interface is active and has addressing attached. Remote routers can be set either manually or statically. Manually or dynamically, statically or dynamically. These are the routes that the router doesn't have a direct connection to and may be learned. So manually, of course, we type it in. Dynamically means that the routing protocol that's put in place means that the routers share information with one another. So when we go back to talking about, EGP, BGP, etc. The default route is where all traffic is sent to a specific direction when there is no match. So that can sometimes be called our route of last resort. A static route has to be configured manually and adjusted manually when the topology changes. This is good for small, non-redundant networks and is often used in conjunction with dynamic routing protocols for finding a default route. So in the event that the dynamic route fails, we have a backup route to say, okay, well, this is what we're going to do. So in the top graphic, we see a manual configuration. We're in R1, we're in config mode, so that's global config. IP route 10.1.1.0, 255.255.255.0, it's our mask. And then we have our next hop, which is 209.165.200.226. So what this is saying is that any traffic that arrives looking for 10.1.1.0 with a /24 mask is going to be forwarded to 209.165.200.226. That's going to be our next step. In the second graphic, we see that the route from R1 to R2 is no longer available, so we would have to configure a new static route via R3, and this is not going to automatically adjust, so essentially we would have a network failure at that point. So static routes are very useful, but in certain cases can be a pain point because we don't always know why the route is not being correctly read. An automatic route or dynamic route will allow us to discover remote networks, gives us the most up-to-date information. We'll often choose the best path to the destination, and when there's a topology change, it can update itself automatically. We can also, of course, share static default routes with other routers if necessary. So if we look at the top right graphic, we can see router 1 is using OSPF to let R2 know about its local network on interface G000. Router 2 is using OSPF to let R1 know about the interface on its usually G000, the .1 interface on both sides. So each network can learn about one another because their routers are sharing information. We can also see in the bottom right graphic that routers 1, 2, and 3 are able to move a new best path if the connection between R1 and R2 fails. Again, OSPF, or Open Shortest Path First, will allow communication between the routers to allow the most easy facilitation of transferring data and correcting in the event of a failed link. So here we have an IP route link showing on our Cisco device or on our router directly. So we can see a couple of codes. L means a directly connected local interface. C means a directly connected network, so L for local, C for connected. D actually refers to iGRIP, so that's the Enhanced Internal Gateway Routing Protocol. O is OSPF, and S is a static route that was manually configured. So directly connected shows as C and L, remote routes show as O, D, etc., and then default routes show as an S, usually with an asterisk involved. We can see a larger expansion of these codes in the table to the right. The default that we see with the static and also with the star is represented by two separate characters. So the star modifier, the candidate default, is actually a modifier of the static route on its own. So if we look here at the gateway of last resort, we see that that is our gigabit 001, 209.165.200.226 goes to network 0.0.0.0. So that's kind of the drain, if you will. Everything else is subnetted so that we can have these routes to go to different computers on these various networks between these two routers. So here are our new terms and commands for this chapter: time to live, ICMP, IPv4, IPv6. We can see the network layer PDU, the IP packet, the header, the ID, flags, fragment, offset fields, and other items from the IP header, flow label, payload length, next header, hop limit, extension headers, best effort delivery, local versus remote hosts, default gateway, traffic class, media independent connection, and a connectionless protocol. Also, we have encapsulation, routing, de-encapsulation, maximum transmission unit and data payload, version, differentiated services, network address translation, and unreliable protocols. In the light blue at the bottom, these are some of our new commands that we will be using in both Windows as well as in iOS. Hopefully this chapter was informative for you on understanding how Layer 3 operates and how we deal with addressing to move information to and from local networks into non-local networks. If you have any questions, as always, you can contact me via email at jearmke063@cfcc.edu. And if you need to, you can of course contact me at my Google Voice number, which is 239-7814. Hope you have a great rest of your day, and if you need anything else, be sure to contact me so that I can correct it before we see each other next class.